Hi, I'm Jim Pivarski. I am from the high energy physics community, and I'm here to talk about a project that blends some of the ideas that are unique to high energy physics with functional programming, which really isn't. So this is sort of a marriage of two worlds. So I'm going to start talking about this by talking about worlds in general. So as I see it out in the machine learning, big data community, there are basically two big clumps of software products. There are the statistical computing with stuff like NumPy, SciPy, R, Matplotlib. And there's big data with Spark, Parquet, D3, Hadoop, and such. The thing that distinguishes these clumps is that everything on the left it's mostly natively compiled for speed with a nice high-level language interface on top. And although a lot of them can be parallelized, the primary consumer is laptop data analysis. That's where it starts and then expands out from there. Whereas on the other side, it's mostly the Java virtual machine running in some large enterprise server, more emphasis on scale out than single processor speed. And the data sets are assumed to be big from the beginning. The very little laptop analysis in Hadoop. So I use that as a segue into talking about a third whole ecosystem that you probably haven't heard of. The set of software tools used by high energy physicists to do things like discovering particles, discovering the Higgs boson and such. So if any of you are in the high energy physics community, have had any interactions with them, maybe some of these things would look familiar. Otherwise, they probably don't. It's really a separate world. Some features of this world is it's overwhelmingly natively compiled. Sometimes they don't have dynamic languages interface on top of that. Some do, some don't. A lot of focus on single processor throughput. And just to split hairs, notice I'm saying throughput. Not speed, not low latency. This is not high performance computing. That would be a fourth ecosystem. So in high energy physics, the reason that they have this whole software stack is because the data sets have always been big. So I tried to find some numbers on this, and the best I could come up with is SPS, which was like the Large Hadron Collider of the 1980s. It discovered the W and Z bosons. That was bringing in about 100 gigabytes of data per year. And so it's the 1980s, 100 gigabytes of data per year. You have to have big warehouses underground with rolls of tape that get spooled up. Today, the LHC, Large Hadron Collider, is bringing in about 25 petabytes per year. It's probably the same rooms, but you know. So for decades, high energy physics, or HEP, seemed to be the only field that had these really big data problems. At least that's how it was perceived, and it was mostly true. And so that's why they developed all their own software. Now, clearly, this is no longer true. Clearly, HEP software needs overlap with the SciPy, R, scikit-learn world, and they also overlap with the Spark, Hadoop, NoSQL world. Individual physicists and projects like Diana HEP, which is my employer, are starting to explore and develop these connections. And this is a very exciting time because what we're doing, we're sitting on a very large ecosystem with a lot of code developed. And we're trying to connect it to another very large ecosystem with a lot of code developed. So it's kind of like sitting between Lake Erie and Lake Ontario and opening up Niagara Falls. You can just write a small amount of glue code connecting two things, and you've just opened up a huge number of possibilities. So let's break down what we're going to do with the software. I would break it into three main categories. Type 1 is high energy physics software that serves exactly the same function as software in the lighter community. And what we would do with something like that is, well, mostly we would replace it. Like the wider community has a lot more resources for maintaining code, catching bugs, and revising designs than physicists whose primary occupation should be discovering particles, not writing code. The second category, domain-specific software for HAP applications. So, for instance, software packages with names like Higgs combiner. Obviously, we would keep that because this really is a unique problem, and it will always be a unique problem. Every field probably has its own domain-specific code. The third type is perhaps most interesting for a conference like this. It's HEP software and also software concepts that would benefit the wider community. And these we want to promulgate. We want to advertise and evangelize. And so that's part of what I'm going to be doing here in this talk. The cultural exchange goes in both directions. I'm going to argue that histograms are an example of type 3. And if you're thinking to yourself, wait, I've used histograms before, this is not new, hear me out. All right. What I'm going to argue is that HEP has a unique and useful approach toward building histograms. But before I go in and spend the rest of the talk talking about histograms, I really ought to define it in case anybody hasn't heard. Histogram is an abstract concept in statistics where you want to approximate a distribution, and you form that approximation by partitioning along one of the features, say like petal length of flowers, and then counting up how many items in the data set fall into each of those bins. And then how you represent that either as the number in the bin with a given, that fit the criteria, or a fraction of the bin is a philosophical debate that people have, but really the data is exactly the same, so I'm not going to do that. As far as I'm concerned, count per bins is great. You can make whatever y-axis you want to make. So now, histograms are definitely used outside of high-energy physics. It's a basic statistical technique. I racked my brain and came up with just a number of statistical packages outside of high-energy physics, and I just looked up their histogram APIs. This was a true experiment. I came up with a list of packages before I looked them up. And what every one of these has is an argument for passing in the input data, and another argument or a set of arguments for describing how you're going to bin it. Now, I'm going to emphasize that point. They all require all of the input data before giving you a histogram object that you can plot. This is the difference. HEP software, and these are all of the packages that I could name that make histograms. Some of them are rather obscure. All of them in high-energy physics treat histograms as fillable containers, not a chart that you plot. The constructor for this object takes a binning, you specify the binning somehow, but you don't put the data in. At this point, you get H, which is an empty histogram. If you look at the bin counts, they're all 0. And then you fill it however you want. And that's important. This API presumes that the data set is too large for a single function call. So you will probably need to you'll probably need to go over data that's on disk at least, because there's no way that the data is going to fit into memory. And you'll probably have to go run this on multiple machines and combine the results later. So just the API is intrinsically single pass. So some of the fancy things that the other packages I mentioned on the previous slide do, that pre-scan to set an optimal bin width or number of bins, you can't do any of that because you could never do that in a truly big aggregation. And just interestingly enough, one of these packages, HBook, I found the first manual was 43 years ago. So they've been doing it this way consistently for a long time, and it's worked out. Moreover, histograms are like the basic building block of all of these high-energy physics analyses. So all of the analysis code are used to build just about anything else. This is just like some random plots I found on the web of things made out of histograms. Some of these are from very old packages. Some of them are fairly recent. When you're thinking about how histograms are used in high-energy physics analysis scripts, you should think it's kind of like lists in Lisp, or dictionaries in Python, or data frames in R. They're used well beyond their original intention. So, for instance, there are quite a few very common things that you want to plot that are made out of these histogram objects, but really they aren't histograms, and a statistician would get all upset if you called them histograms. The first is arguably a histogram. It's stacked histograms. Like if you want to make this plot where you're showing the data and then simulations of all the different kinds of contributions that you get to that data, you stack them by, you make 8 empty histograms. One of them you fill with only one contribution. The next one you fill with the first 2 contributions, all the way up until the last one you fill with all the contributions, so that when you overlay them, it looks like they're sitting on top of each other. In fact, you can see that this one here has been reweighted, and it's sitting on top of that lower curve. You can make efficiency plots, which is the probability of passing some filter as a function of some variable. This is in no way a histogram. But you can make it by filling 2 histograms. One of them is called numerator, the other one is called denominator. And the numerator, you apply the cut. Then you do bin by bin divisions to make that plot. There are profile plots, which is like a slice in a dimension of the data, where in each one of these bins, each one of those crosshairs there, is the mean and standard deviation of the y data in a bin of x. And you build that by filling the histograms with sums and sums squared. Now, the reason I wouldn't advocate going and using this API exactly as is that there is a problem with it. And I'll explain how we encountered that problem that hadn't been encountered for 43 years. The problem is that domain-specific knowledge enters in 2 places. First, you need to know something about what it is you want to aggregate in order to set the binning strategy, in order to set a reasonable binning strategy. Then you need to know the domain-specific knowledge again when you're actually filling it with values. You have to compute those values. And interestingly enough, in the merging, if you did this in parallel and you want to merge jobs, that does not require any domain-specific information. And that part is easy. So we ran into this because we're trying to do some high-energy physics data analyses in Apache Spark. And Spark has a functional API. The traditional interactive analysis script would look like the thing on the left, and the Spark equivalent is on the right. So here you have the constructor, you have a for loop that you fill, and then you can plot. The Spark equivalent, you have an aggregate method that you give it an empty container, and it sends that to all of its nodes, and it runs an increment function on it, and then it pulls the results back and combines them with a combine function, adding them together. And you can just fill in the blanks that this is where you put the constructor, this is where you put fill, and this is where you put add. That's fine. The problem comes in when you want to make multiple histograms. And a typical analysis script, a few hundred. Lots of different things you want to look at, lots of different views of the data. Then the problem is that this increment function has to get the histogram as an argument into the function, and has to return it as a return value. Because over here, you just use global state. X, Y, and Z are global variables, and you fill them. Over here, they have to be passed in every time you call the function and pulled out of the return every time you call the function. And you can do that by making a tuple and having tuple indices, but it's looking kind of bad for 3 histograms, and what kind of indexing mistake you might make here and here. It gets even worse if you have 100 or 200 histograms. So, solution to this, the way that we can get the best of both worlds, is to augment that original design, still have this thing where we are we construct an empty histogram and later fill it. But now make the constructor a higher order function. Let it take a fill rule as one of its constructor arguments. And the fill rule describes how to take each datum and turn it into a value that you bin on. You use that value to decide which bin should get incremented. So now, all of the domain-specific knowledge is in the constructor. And you can just fill it blindly, right? You don't need to know anything about the particular physics analysis you're doing in order to fill it. Oh, and by the way, I'm using fill as an in-place operation. If you're working in a purely functional environment where that's not allowed, it's easy to talk about non-in-place operations. That's sort of orthogonal to this. So here's what this looks like in Spark. You can define in a library once and for all increment and combine, because they don't involve any domain-specific knowledge. And then in aggregate, the binning and the fill rule are domain-specific knowledge that go into the constructor. And then increment and combine are just your library functions. And then where that helps you when you're trying to scale this up to a bunch of different histograms is you can make, I'm going to call this class label, because it's going to make a bunch of labeled histograms, named histograms. You can write this class also in the library, once and for all. It's something that has the same interface as a histogram, fill and add. And so you can construct a package, a group of histograms with this nested constructor. But the increment and combine functions are exactly the same increment and combine functions. You didn't have to use a different one. So we can do an elaboration on this. Sorry, one slide behind. So the thing I want to emphasize about it is this packaging label has the same interface as histogram, namely the fill and plus methods. And so histograms and collections of histograms are now interchangeable. So here's how we elaborate on the interface. We could imagine making a lot of different aggregators in general, the generalization of histograms, and aggregators that you can compose. So to make the example on the previous page, we can split histogram down into its basic atoms, bin and count, because a histogram is binned counting. And you can just imagine composing those two, just like you can compose the histograms in the label thing. And with the right set of aggregators, you can build anything you want. The first of these is a traditional histogram, bin of count. So there the constructor has the binning rules and the fill rule, and then what we're saying that's new about it is that the values should be counts. Now, you can make two-dimensional histograms, which you might think of as heat maps. You can do that by doing bin of count, because what's a heat map other than a histogram in X, where each bin contains a histogram in Y? That's a heat map. And then, so bin of count. You can make the profile plots I was talking about by replacing count with some new aggregator called deviate that aggregates a mean and standard deviation. You can mix and match different binning methods. Irregular binning if you want the spacings to be different. Sparse binning if you have something like a hash map of counts instead of an array of counts. Categorize, this is what I call if the bins are actually strings, categorical strings. You might know that as a bar chart. You can make complex trees of whatever it is you want to build up. So here's one where I bin something in X, and that in each bin I put a count, minimization, a maximization, an average, sum of weights squared, because these are useful things when you are doing some advanced statistics. Actually, in those histogram packages, I didn't mention, a lot of them are doing things like collecting the sum of weights and the sum of weights squared because they know that users are going to want that, but that was hard-coded in. Now it can be constructed. You can have high-level interfaces to common patterns. Like the efficiency plot I showed before, you could create an aggregator called fraction that builds that for you. Or the stack plot, you could make an aggregator called stack that builds that for you. And the advantage of this is that it guarantees that the bins of the contained object will align because they are cloned. So a package that does this is called Histogrammar because the compositional thing is kind of like a small grammar. And so the website for this is histogrammar.org. Histogrammar is a suite of composable aggregators with a language-independent specification. So if you're wondering, is this just a Spark thing? No, it's not. It's supposed to be general. Several language versions. Python and Scala are the most complete. An interchangeable JSON format so that you can get data that has been aggregated in one system in one language and move it to another system that maybe has better plotting tools. So you can plot data. I call it a plot data that comes from hard-to-reach places. Multiple filling backends. I'll show a couple examples of those. And this package has no built-in plotting because there are plenty of plotting libraries out there. Some of them within the high energy physics world, and some of them, Matplotlib, Bokeh. There are plenty of plotting libraries. So I'm just going to call these front ends and translate these objects into them. And then you can use whichever one you want. So from users' perspective, the user has something that they want to aggregate. And so they think about how to express that in these composed aggregators, which is kind of a declarative language. The constructor, you could imagine the constructor expression, the nested thing is a language. And then you have multiple filling backends to choose from, depending on where the data are that you want to aggregate over. And then you have multiple plotting front ends. And I would like this list to grow. So it's like this octopus that's got its fingers in everything, right? And that's also how this is acting as glue code between the high energy physics world and the big data world, because if this package has its fingers in both, then it can get data across. Coverage, not important other than just showing that this is how we think about it. On the rows, those are all the aggregators. And then whenever you start a new language or a different kind of backend, you just go down the line, implement each one, and then it's interchangeable with all the other systems that know about histogrammar. These global question mark is because on the GPU, you have to think about how you can deal with an algorithm that is not fixed memory. And so maybe there'll be a solution for that. But actually, if anybody has any ideas, I'd like to hear. And it's designed from the very beginning for distributed workflows. Like this was the motivating example. In Spark, he wants to fill in parallel, combine, and then get everything back down to the head node so you can plot it. If you are analyzing data on GPUs, well, it's exactly the same picture, except that now, instead of having a head node and executor nodes, you have host and device, your CPU and your GPU. So same concept, it really should be some of the same code. These are some screenshots from the specification just to show you what's up there. A lot of introductory material, exactly laying out what the constructor arguments should be in each language so that it really is interchangeable. Laying out what the fill and combine methods should be. And to make this really explicit, I decided to write them in very simple Python. Not very performant Python, but just to show exactly what it ought to do. And so we can do cross-language testing to make sure that they all do exactly that. The JSON format is fully defined, and this is what a traditional histogram looks like. The JSON format was designed so that you can read these. Okay. So, want to check on things? Okay. So, and then the tutorials page, there are tutorials for getting involved in this, for getting started as a user. If you start playing with this and write a blog on it, please tell me, and I will link to it from here. Because I just want whatever kind of introductory material is useful for somebody. So some examples of these backends. In Spark, if you are working with RDDs, you provide an opaque function. This is a Scala function. You make bin of the counts is the default. So you're making a histogram by just saying bin and give it a function. And then the new increment and new combine is doing some Scala type stuff in order to infer all the types from that. Spark SQL, you write them down as the Spark SQL column syntax with the dollar signs in them. If you're familiar with Spark SQL, this should be familiar with you. You can just put that right into the constructor. In Python and NumPy, you can write them as strings because in Python you have eval. It has a NumPy optimization that is for some of these aggregators much faster. The Python has a JIT compilation backend that generates C++ code on the fly and compiles and runs it in LLVM. But now the difference is that it has to be a string and it has to be C code that goes in there. And this is consistently faster. In fact, it's also faster than generic C++ code. GPU is a special case of JIT that actually I think I'm going to zip by, but if you are developing GPU algorithms, you can use this for diagnosing. Now, last thing I want to talk about is some problems we encountered along the way because we just started into this with making what aggregators did we want and didn't realize that certain mathematical properties have to be maintained in order to be able to have them be composable like this. So I learned along the way that all the aggregators must be additive so that it's independent of whether the data sets are partitioned. It must be homogeneous in the weights. I didn't say that you fill with weights, but you can do that. And so you can fill with a weight of 2 to get the equivalent of filling twice. These properties taken together is often called linearity. It must be associative, so it's independent of where the data sets get partitioned. And it has to have an identity, a 0. So this is a monoid. So all of these aggregators have to be linear monoids. And then your result doesn't depend at all on how the data is partitioned. We had to kill a couple of desirable aggregators because they didn't adhere to this. And if you are mathematically inclined and can think of any algorithms that would satisfy those properties so that we can get aggregators that do that, I'd very much like to hear it. Finally, want to get involved? Here's a website. It's got everything that you need. This stuff is up on Maven Central and PyPy. You can run it today. Do you want to do interesting things with it? Like, do you think it could fit into your application? Do you want to wrap Histogrammar Scala as Hive UDAFs so you can use them in Hive? Do you want to, we'll do any of those things? I'm running out of time. Then please talk to me. I would love for the octopus to have more tentacles. Here I just thought, write up 8 more things I'd like to see. Especially like to see a Unix command line tool so you can awk into it. So talk to me after this if you're interested. Okay, we've got the full 10 minutes for questions. Yeah, in the back.
You mentioned about being able to query in Hive.
What was it?
Being able to query the histograms in Hive?
Yes, being able to make histograms in Hive would be wonderful.
Okay.
Right, that is a potential project. But you see, you've got the Scala code, so you just have to make UDAFs. They're all aggregation functions. It's just a matter of wrapping it up and making sure the types match. Mm-hmm. Yeah.
So Histogrammar is a language-independent grammar for putting together histograms.
Yeah.
It seems that in the language, part of the constructors took arbitrary functions as arguments. Are there any restrictions on those functions that you would expect, or like conclusion follow?
Yeah. So the question is, are there any restrictions on the functions that go in? And that's language dependent. No, that's kind of not. Independent of language, they have to be consistent with one another. So if you're aggregating over a data set of events with type D, and your functions all have to have an argument of type D, right? This is enforced in Scala, not enforced at all in Python, right? It's duck typed. Not enforced in Julia, because it happens too late. Yeah, it depends. Like how it's enforced depends.
Right. And other than the type, are there any like operations within that function that you would say like probably should do like something that is gonna do I/O and
Oh, yes. You shouldn't make functions with side effects.
okay.
Yeah, because you don't know for different backends when and how these are going to be computed. In the NumPy backend, for instance, it does one histogram bin at a time. So it starts at the first bin, does everything in there. Second bin does everything in there, which is a completely different order than if you were going through the data row by row. Yeah, so you shouldn't have side effects. But this is functional, so.
Have you tried any use cases where you use approximate counting as the fill mechanism?
Yeah, so that was what was wrong with both of these. Both of these adaptively binning to determine the binning strategy as you go along in a one-pass, like these incrementing histograms way. Actually, the algorithm I used there is the same one that is used in Hive. And quantiles, that's also adaptive. The problem with it being adaptive is that it's history dependent. So if you partition differently, you'll get different results. They will be approximately the same. But now, if you go on some 10-node Spark cluster that is going to partition the data into 10 bits, or a 1,000-core GPU that's going to partition it much finer, you'll get very different results. And we don't want that. It would just be unreliable. More questions? Yeah.
Have you ever played with streaming data, like coming into
No, that's that tentacle over there. This would make a great, actually it's two of them, a streaming tap. Like if you want this to be tapped onto some bolt in a storm network, and just watch the data as they go by and aggregate it as it goes along. And then outside of the storm network, send the aggregated results, because remember, they're small. They're just these little JSON objects, to something that's continuously fill some animation on a dashboard. That would be cool, right?
So you see sort of the histogram revolved.
Yeah, right. In fact, in the high-energy physics applications, when I often would just rapid-fire plot the histogram as it's filling, just to see it go up, and hit Control-C if it's not what I wanted it to be. Then I don't have to wait for the whole thing. Right. So yeah, please talk to me if you are interested in any of these extensions. The involvement can be a little or a lot, depending on if you want to write some new language implementation of it, or if you want to just tie in something to your favorite application.